Hey everyone, this is Dr. Walker. This is video 527, determining the field from the potential. So in video 524, we were able to find the potential difference between 2 points A and B if we knew the electric field between those 2 points, and we did the integral of E dot ds. So now we're trying to do the opposite. If we know the potential, how do we find the field? So from this equation, what this tells us is that dv is just what's inside the integral, negative E dot ds. And so let's just consider the case of a point charge that we're very familiar about, and we know that the electric field is in the r direction, it's a radial electric field. So if we're looking for E dot ds in the case of a point charge, we know that this is going to give us ER, right? E sub r, it's in the radial direction, dr, right? Where dr is the component of ds that's along the field direction. And so from this, we can see that ER is going to equal negative dv over dr. As we expected, the electric field is the derivative of v with respect to r. But in general, the potential can be a function of all three coordinates, not just r. It can be written, for example, in the Cartesian coordinates. That's what we're mostly going to deal with when we're doing these types of problems of finding the field from the potential. So if the potential is in Cartesian coordinates, then we could write three separate expressions, right? E sub x would be negative partial of v with respect to x, etc. So if we know the x, y, and z components of the electric field by finding those partial derivatives, then we can write the electric field vector, right? We can just write all of these components and we can say, okay, the electric field, we can factor out the negative here, is going to be the negative of the partial of v with respect to x. That's going to be in the I direction, plus the partial of v with respect to y in the j, plus the partial of v with respect to z in the k direction. So when we write it like this, then we actually have a more simple way to write it, and that is to replace all of this with what is called the gradient operator. So this symbol right here is the gradient operator. So instead of writing the electric field with all of these partial derivatives, we can replace it by the gradient, which is written differently for the various coordinate systems. But as I mentioned, we're mostly going to be dealing with the Cartesian coordinates for these types of problems. So now we have a really nice expression for the electric field. It is the negative gradient of the potential. And we're going to do a few examples of finding the field from the potential in the videos that follow.